Alright, hello and welcome to Florida Man Math. In this video, I'll be showing how to construct two types of 4x4 magic squares and show a little bit why they work. The first type of magic square we've got works really well for a date in the form of month, day, and a year broken up into what we're going to call the century, and then the last two digits are the year. So I've color-coded the letters to make it clear. So the whole point of this is to make the top row for a date in the form of month, day, century, and year. And let's make it more interesting by rearranging some of these values such that they don't ever repeat a row or column. So we'll start off by putting an M here, and an M there. Moving on to the day, we'll keep the original here. Next row goes there, next row, and last row here. And what we're calling the century, which is the first two digits of the year, we'll start off with our original, next row, third row, and fourth row. And finally, the last two digits of the year. There's only one spot left, so let's just fill those in. All right, and so let's take a look at the top row here. What makes this a magic square is about the sums of different directions and different sections of the square. So for example, if you add M plus D plus C plus Y, you're going to get some capital N as a total sum. And as we established before, because we don't repeat any row or column, each row is only going to contain one of each color / letter here. So you can see that this sum is just a rearrangement of the top sum. So this will be adding up to n. Similarly, the same argument still applies to the third row. No repetitions, and each color is represented. So this adds up to n. And exactly the same argument here for the fourth row. No repetitions, each color represented. So all sums to n. So that works well for rows. But like we established for all the rows, it works exactly the same way for columns. So going down, we've got all four colors represented. So all the letters are just rearrangements of the sum. That adds to n. And just checking the second column here. Yep. And it looks like we're in business for the third column too. And it checks out for the fourth column. And what makes it even more interesting is that this applies to the diagonals as well. So looking across here, we've got black, green, purple, blue. So that adds up to our total n. And it works on the anti-diagonal as well. Green, black, blue, purple. So we've got all these different sums of n around, which is nice, but we can do even more. Take a look at the 2x2 square here. Each color is represented, no letter is repeated, and so this will actually add up to n. So let's indicate that like here. And let's take a look at this 2x2 square. Same argument applies. So we have a total sum of n here. And you can actually find this in several other places across the square. Here's another 2x2, adds up to n. And yet another 2x2, adding up to n. And by symmetry, this works out nicely too. And we've got another 2x2 in the lower right corner here. So unfortunately, it doesn't work quite here because these numbers aren't representative of all four, and similarly that doesn't apply down here. But it is kind of neat that there's sort of a checkerboard pattern. You've got D and C alternating and M and Y alternating. And nicely we actually have a central sum with all four of these represented. So out of all the possible arrangements of four things, this is pretty dense when it comes to all the different occurrences of n across the rows, across the columns, both diagonals, and several of the 2x2 squares, including the central one. So we're only missing these two, and they form the aesthetic checkerboard. So by itself, we could stop here, but all we've done so far is really just rearrange the numbers. So if we kind of adjust them, we can make the square a little bit more interesting. So let's talk about deviations over on this box. So we want to keep the top row the same. So let's not adjust it whatsoever. So we'll have 0 deviations. Now, some of these we want to adjust by adding some numbers. So let's add a +1 here, +2, and +1. Over here we'll have +3, +2, +1. And now if we're going to keep the total sums across all of these different ways to get the capital N, we have to basically have a net sum of 0 across rows, columns, diagonals, etc. So we need to cancel this -1 out with that. And we need to cancel that +3 out. Need to cancel that +2. Cancel out that +2. And cancel out these 1s. And so you can check for yourself to see that across all of these, the net sum adds up to 0. We've got +-1, cancel, cancel. We've got a bunch of +-2s canceling. +1, -1, +1, -1. So the rows are a net change of 0. How about the columns? So the top row doesn't contribute anything. So we've got +1, and then -2. Net change of 0. Net change of 0 here. Net -3, but then +3 here, so that's 0. And then +3, -3. So there's no net change across the columns either. Let's check the diagonals. So across this diagonal, we've got -2, +2. So a net change of 0. And the anti-diagonal, we have +3, but then -3. So that's good. Net change of 0 across the anti-diagonal. And now let's check all the 2x2 squares corresponding to these circled ends here. So there's a net change of 0 here across these 4. There's +1, -1, -2, +2. So that's a net change of 0. Same argument applies here. In the middle, we've got a -4 across these, but then +4 across these. So that's a net change of 0. Over here, we've got 0, 0, -3, +3. Across these 4, we can see those cancel out. And finally, these cancel out similarly too. So we've got 2 sets of magic squares, and now what I want to do is combine them so you have the original month, day, century, year magic square in all of its properties. And all we're doing is overlaying these deviations across to match up with this square here. So I've gone ahead and merged those in the form to match the colors. So we've got the month and its deviations are in black. The days and their deviations are in blue. What we're calling the century has deviations in green. And purple for the deviations with the year. So let's try an example. So let's say you wanted to wish your friend a happy birthday on June 26th, 2021. So what we should start off with is the numerical equivalent for June. So month will be equal to, June is the 6th month, so we'll take 6. The day, of course, is simply just the day. D equals 26. And what we're labeling the century is the first 2 digits of the 4-digit year. So C is equal to 20. And finally, 21 is the last 2 digits of the 4-digit year. We're labeling as Y. Y equals 21. So the whole point of this is to have no adjustment across the top. So we want M is equal to 6. And then let's fill out the deviations first. So we've got M plus 3 6 plus 3 is 9. M plus 2. 6 plus 2 is 8. M plus 1. 6 plus 1 is 7. Now let's switch over to the days in blue. So we'll start off, so 26. And then D minus 3 is 23. D minus 2, 24. And D minus 1 is 25. All right, moving on to what we're calling the century. C equals 20, so it's unchanged in the top row. We're subtracting 1 here, so that's 19. We've got subtracting 2 over here, so that's 18. And then C plus 1 here, so that's going to be 21. Finally, we need to take care of the Y, which is unchanged up top, so that's going to be 21. Plus 1 is 22. Y plus 2 is 23. And then subtracting 1, we get this here. So here is your magic square for the format June 26th, 2021. Now this format with month, day, century, and year that you could use from this template, occasionally you might get negative numbers, and that's because these negatives go up to -3. So you might get negative or 0 days depending on if your month or day is a January, February, March, or it's the first, second, or third of the month. So again, we have the sum across the row here is n equals 73. And we can check that that's true across all the rows, all the columns, both diagonals, and each of the 2x2 squares touched by these 7 points. And so again, the magic number for this magic square for June 26, 2021 is 73. Now, not every country uses this format of month, day, century, year. Some countries use the alternative format, which is probably more popular, which starts off day, month, century, year. So I've changed everything to match up with the colors, such that day comes first, and it's in black, and month comes second, and it's in blue, and provided the example for the same date before, which is 26th of June, 2021, and you'll find that example filled out here. And because we've only changed the order of the numbers, we haven't changed the numbers themselves, nor their deviations, you can go through and verify that each of these numbers add up to the same number here, which would be n is going to be 73. And so that'll be true across all the rows, all of the columns, both of the diagonals, and across these 7 points for grabbing each of the 2x2 squares that they touch. So the sum for, or the magic number for this magic square is 73. Okay, so now we're ready for the next 4x4 magic square format. And in this variation, we're going to start off with the numbers that are fixed on the first part, and then we'll insert the number n. So this magic square is based on the idea that you choose a target number n, and each one of the rows, columns, diagonals, and several 2x2 squares add up to that target n. So let's start off with the positive numbers. So we'll have 1, and then 2, and then 3 here, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So these numbers are going to be fixed the entire time. They're all the positive numbers. So there's a lot of green here indicating positivity. We need to cancel everything out, and so we need a number such that this 2x2 square and column and row and diagonal will be 0. So let's cancel that out. We've got 1 and 12, it's 13, and 7 is, we need negative 20 to cancel these out, and all the other directions too. And for this spot, we've got 11 and 8, which is 19, plus 2 is 21. So that's one way of verifying this should be negative 21 to 0 out this row. For this third row, got 5 and 10 is 15, plus 3 is 18. So we'll cancel those out with minus 18. And 4 plus 6 is 10, plus 9 is 19. So canceling out with negative 19. And it's easy to see that each of these goes to 0 like we wanted for the rows. And we can also verify that for the columns. 11 and 5 is 16, plus 4 is 20. That cancels out here. So that sums to 0. 1 and 8 is 9, plus 10 is 19. Minus 19 cancels out. 12 and 3 and 6 is positive 21, cancels out with minus 21. So that zeroes out. 7 and 2 is 9. Another plus 9, but then minus 18 also cancels out. So let's take a look at the diagonals now. We start off with a minus 20, but along here we have 8 and 3 is 11, plus 9 is 20, so that cancels out. And let's look at the anti-diagonal. 4 plus 10 is 14, a plus 7 up here is positive 21, but then it zeroes out with negative 21 here, so that's 0. And let's take a look at the 2 by 2 squares. So for example, this 2 by 2 square, 11 and 8, 1 is 20, zeroes out with that 20. Over here, we've got 15, 19, so that's a 0 here. And how about here? 1 and 12 is 13, plus 8 is 21, cancels out with that. So that zeroes out. Let's try the center. 8 and 10 is 18, plus 3 is 21, cancels out here. Down here we have 10 and 3 and 6 is 19, minus 19 cancels out there. Back up here we have 12 and 7 is 19, plus 2 is 21, minus 21, another 0 out there. And over here we have 3 and 6 and 9. That adds up to 18, cancels out here. And the only deviation here from all these nice cancellations are these two 2 by 2 squares here. And if we look at their sums real quick, we get 11 and 8 is 19, plus 5 and 10 is 15. And so this ends up being 34. But if we take a look at the other side, we get 3 and 2, which is positive 5, and then minus 21 minus 18. So that's negative 39. So negative 39 plus 5 gives a negative 34. So at least it's symmetric, even though it's not 0. So those were the fixed numbers. Now let's take a look at the target number. And so this is the number that we want the magic square to sum to, because we've seen that this really just has a bunch of net zeros floating around. So we have our target number n. That's going to be the magic number of this square. And we want to avoid repeating rows and columns. So we'll arrange it like this. And then we'll fill out everything else with a 0. And it's tempting to find the word noon somewhere, but as we pointed out, there's no repetition of the letter n in any row or column, so it's all just n's and a bunch of zeros in every direction. And this one is much easier to see where the sums come from. This adds up to n. This adds up to n. Also adds up to n. And going by columns now, because none of these n's are repeated, they all add up to that target number, magic number n. Let's take a look at the diagonals too. There's just an n there, going in that direction, we see an n there. And taking a look at these 2x2s, much more immediate. For these 2x2, we get n. This one adds to 0. This is n. For these 2x2, we get n. For the center, we get n. For this 2x2, we get n. Up here, we also get n. Here we get 2n, so that's a bit of a deviation. And then back to n down here. So altogether, the only deviations are really the 34 here, negative 34, and a 0 here, and a 2n here. So other than that, though, these magic squares have either a magic number of 0 all the way around and inside, or they have simply the target number n, except for these slight deviations. So let's overlay both of these into one combined magic square. And you'll see the only things that are changing are when we adjust the number n. So all these numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, those are going to be fixed. So let's do an example. Let's say we want to do example of n is equal to 25. So it's just a matter of plugging and chugging for these 4 cells. So you can fill out the constant numbers first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And now that we've done those 12, we can fill in the constants. So n minus 20, 25 minus 20 is 5. N minus 21 is 25 minus 21, which is 4. N minus 18, which is 25 minus 18, 7. And finally, n minus 19 is 25 minus 19. And so that leaves us with 6. So here's our magic square for the sums adding up to n is equal to 25. And that's true in that direction too. It's true in the rows. It's true for the columns. Also true for the main diagonal and also the anti-diagonal. And each of 7 central 2x2s. So we've got our 25 here, got 25 there, 25 across the top, in the center, in the middle, upper right 2x2, and lower right 2x2. And again, remember that the only deviation here is that these always add up to 34, and this is, in general, 2n minus 34. So that'll be 2 times 25 is 50, minus 34 is 16, and we can verify that in another way too. 4 plus 7 is 11, plus 5, 16. So there's the 4x4 magic square, where the target number n is the one you choose, and then you generate it so that each sum appears all the way around and inside here, with these 2 slight deviations. So now you might notice that some of these numbers repeat. So here we've got 5 repeating, we've got 4 repeating here, we've got 6 repeating, and 7 also repeats. And so the question for you is find the lowest number n such that none of the numbers repeat and they're all positive. And so leave your answer in the comments, and I hope you enjoyed this video. If you want more like it, please hit like and subscribe, and I'll see you next time. And as always, thank you for watching.